134 degrees or 134 degrees clockwise.
Yeah.
And I'm like, you know what? Just kiss my booty.
That's the beauty of all that computer programming stuff.
Have a good one, sir.
You too. Okay, I think I'm in here. Now I'll go back to here. And now I'll go to here. So we're about the point of curb gates. So, oh, did you have any? Oh, let me tell you what. So what I'm going to do is I'm going to take, I've been setting it up so we have 2 assignments every week. One that's classified as homework, one that's a quiz. I'm just going to put them together and call them a homework. So, and then the grades will just be put together. Because, I'm finding that some people are rushing to do the quiz and then doing this and that. There's just, and I've noticed, a couple people will like, oh, I'm going to go do a quiz and then something happens. But it's just too much hassle, I think. Too much hassle for me, too much hassle for you guys. I'll just make it so there's 1 assignment every week. And it's just, I'll call it homework quiz or something.
Okay. On the last quiz, one of the problems I got wrong. I don't know which one I got wrong.
Uh-huh.
I just know I got it wrong.
Oh, okay.
And I would like to go back and figure out where I screwed up on it.
Okay, so let's see if we can find it. Wait a minute. There. I hope I went to the right place. There. Is that it? So you don't know which one. But would you recognize it if you saw it?
I mean, I want to say I got that one right, but...
Let's see. Let me do standard view. And then... Okay, so there's that one. Was that?
I got that one right, too.
So maybe it was this one?
Probably that one.
Okay. Let me see if I can... He does a little better job here because now that I see this is probably... Oh, my time's up.
Time's up. Yep, can't do it.
Okay, so let's see. It's clipped part of it, so let me see if I can bring it back out. I can maybe... Okay. So the water is filled, no, the container is filled with water at 25 degrees at a depth of 2.5. Container has a mass of 30. The density of water is that after 25 figure. So he says all that. Determine the combined weight of the water in the container in the water. Okay, so combined weight of the container in the water. Okay, so let's start with, he's got pi diameter squared over 4, that's the area of this top thing, times 2.5, that would be the volume. But if I wanted he wants the weight, so if I wanted the mass of the water, or whatever that is in there, yeah, it's water. It's 900, so this would be in meters to the cube, 997.1 kilograms per meter to the cube. But that's still not the weight. If I multiply, that's the mass. And then I'm assuming, this is an assumption, meters per second squared. I'm assuming it's 9.81. Then he says the container has a mass of 30 kilograms. So really, what I need to do is I need to add 30 kilograms here, and then multiply that times 9.81 meters per second squared. So I do all that, and then I put this in. Let me see what happens when I put, I think I have MATLAB up, I think. I did.
Yeah. at one point.
Oh, I don't. Here. So it's not that. Okay, so that's where I was. So let's see. 9.81 times, and I have a difficulty going back and forth. Pi, that'll be pi over 4, the 1 squared times 2.5 is 2.5, and all that times 997.1. All that, and then that'll be plus 30 kilograms. Oops, 30 kilograms. Okay, let me steer it, make sure I copied all this down right first. 9.81 pi over 4 times 2.5 times that gets me the number of kilograms of water, and then I got 30 extra kilograms, 9.81. So this says 1, here, I'll write it over here. 9.5. Okay, wait a minute. Say 1, 2, 3, 4. 19500. The question is going to be Newton, or is he going to want 19.5 kilonewton?
Yeah, it's gonna. See, that's another problem I have. So does it want? Will it take kilonewtons?
That's a
Because I
good.
ain't got it to take kilonewtons right yet, and I always convert it back to newtons, and then it counts it as right, but it says my sig figs are off because I convert it back to newtons, not kilonewtons.
Oh, okay. Oh, I see what you're saying. Okay, subscription acceptable unit list. Okay, so we're looking at a weight here. Do you see weight in there? Or it should be force. Force.
Force, yeah.
Okay, so that's really weird. Let's see. There's Newton.
But I never see
Wait,
kilonewtons.
Newton. I don't see a kilonewton either. He must not like kilonewtons. So I think we better
So I
stick.
just put newtons in, and it counts off for like the sig figs, like saying technically we wanted it this way, but your thing is equivalent.
Oh,
The way it's
okay.
been doing for me.
Okay, let me see if I can go back to where the problem is. Here it is. So I'm assuming if he wants Newton, that's going to be N. And 19500,
Yeah.
not compliant. Oh, what? So I can't enter it because the time's up.
Yeah.
Previous answer?
You don't have one.
Oh, okay. How do I do this then if I can't? I'll tell you what I could do. Could do something. Since I'm basically making things, I'll go ahead at the date so I can enter the answer. Due date was today. Today is the 21st, right? At midnight. We're just going to change it. That way I can go put in the answer. It probably will make me refresh it. How do I refresh it? F5 maybe. Hey, I can do it now. And nothing changed, did it?
No.
Okay. 19500, wasn't it?
Yes, newtons.
Submit. Huh?
Simon timer's not running apparently.
Here, I'm going to request the answer.
Okay.
Okay, there you go. Timer's not running. Okay, so maybe I need to go back and start the test again. Here, let's try that. Okay, there it is. What was this? This was the problem.
Yeah, that one. Nope.
Oh,
nope.
wait, okay, it just started me in the test. Why is my timer not running? Oh, because I'm in the wrong view? No. Wait, standard view. Request the answer. I can't
You
do.
go in as a teacher and view the answer.
Yeah, I don't know that they let me do that. Let's see. Solution view.
Ah, that might be helpful. Yeah.
Well, now he says killing it.
Yeah. How do you know when to do what? Is what I guess I'm trying to ask.
I don't know. Well, I would say get your points, and then I'm gonna basically, it's not gonna be, now if you get a 0 on everything, that's different, but if,
Yeah.
whatever it is, I'll
Okay.
just,
I'll talk to you about it.
yeah,
That's fine.
don't worry about that much. Okay. Yeah, I don't know, and he doesn't have, if you look over here, I do not find, I mean, okay. If you're going to put in kilograms, then I would assume he would list that it would be kilonewtons. But, I mean, here, kilograms, I don't know. Oh, wait a minute. Okay, wait, enter that, enter this. So he's telling you, oh, he doesn't have an entry outside of this and this. So does that mean you just enter G or, okay, A, atomic mass unit, AMU. I don't know. Yeah. I'm not sure.
Well, I was off due to rounding anyway.
Oh, okay.
Yeah, it was. I put 19,490.59 newtons.
Okay.
Because by the time you do your rounding up, it goes up to 19.5.
All right. So it we left off in the problem set. And I don't know that we officially covered curved gates, so let me do that real quick. Trying to find it on a curved gate. But there's an interesting way to think of this that may be better to do than what he's got here. And let me just, and to make it easy and quick, let's just, okay, I'm gonna do MATLAB because then the whole screen will be white. And then I can write there, okay, so here. Okay, so let me just show you a mental approach. There's two mental approaches that work very well. And the best way to do it is just with an example. So curved gates are, the ones that are mostly interesting are cylinders, half cylinders, in this case a quarter cylinder. Let's say you put water, so you have some sort of concrete, that's a hinge. So that's a little hinge point. So you're interested in this, say it's 2 feet in a radius there. So you put water on, let's say you put water on this side first. So you put water on this side. Over here, you got air, and you're pushing up on the thing to keep it closed. So maybe there's a concrete piece right there. So there's concrete there. So you want to know what the force that concrete's pushing back up on the gate so it won't crack it. And so the way to think about this is, if you could take a block of ice, and if ice has the behavior when it freezes, it'll float. But let's say you had it so that it was a little bit different. You took a box of water and you just you filled it with water, the box didn't weigh anything, and you just left it there. It wouldn't move up or down unless there was waves coming. It would be pretty much neutrally buoyant. And it would just be a box. Now, if you imagine that you have a box sitting over here, so here's your box. Okay, I haven't done a good job of drawing my radius, so my radius goes to right there. So now imagine you've got a couple of boxes. You got a box that sits right here, and you got this box. Well, the box over here, just like the box everywhere else, has a weight to it. It just so happens that the weight in that box is equal to gamma times the volume of the box. But this time the box is this shape, and this time it's a funny shape. It's a half cylinder, so actually it goes back a certain distance. In other words, so say it goes back like that. It goes back like that. Here's your gate sitting on this concrete thing here. So actually, technically, this goes back. And so you got this box. So if you found the center of it, this weight would be equal to, let's just put numbers on it. So it's 10 foot from here to here. So same thing, 10 foot from there to there. This was 2 foot. Seems awful big, so I'm going to make it 5 foot instead. So the weight of this box, I'll call it weight 1. And then there's a weight in this box. And this box center is over here. So it's 5 feet. And its weight is right there. So now I'm going to get rid of the perspective view again. So I'm getting rid of the perspective view, going back to just the side view. So we're looking down at it. It's 10 foot. And say it's only 1 foot into the board. 1 foot into the board. Or maybe let's make it 2 just to be complicated. Just so that you know that there's 2 foot into board. So the weight 1 and weight 2. So now the weight of the box there 1 is equal to gamma of the water, because it's neutrally buoyant, and the volume of that, which that volume is 5 foot, because it's 5 foot across here. It's 10 foot tall and 2. So that's 100.
5 times 10 is 50 times 2 is 100. Yep.
So let's just say this is water. 62.4 times 100, which is 6,400 pounds. So that's the weight that's right there. Now that's bearing down on the stuff below it. So this has to hold that up, as well as some force coming to the left. So now you have this neutrally buoyant block and another block, but it's actually somewhat being pushed against the wall there. Now, this block is shoved against this wall, and then this wall is strong enough to hold back against it. This block is shoved against this thing. And it's like so. So we're interested in what's the force on this thing. Let me go in and do the weight of block 2, which is 1/4 of pi r squared, but r is 5 foot. That is the area here, and it's extended back by 2 foot, and it's the gamma, 62.4. So this is the volume of the volume of quarter cylinder, and this is the gamma, and that'll give you the weight of that. So you calculate that. Okay. Any clue what that would be?
2,450 sound about right?
We have 2,450. Give me a bunch of digits.
0.44227.
Okay. I'll show you why we're doing the digits in a minute. We're going to do extra digits. Okay, so that's, if you did a free body diagram of just this gate now, what you would get, you'll get, of course, a hinge force, HY, and say HX. And let me put the HX on the other side. And we'll sum moments about there anyway, so we don't care. But I've got a weight that comes straight down here and one that comes straight down here. Then I actually have this over here, and I have the result. And what I'm going to do now is break down these into 2 components. Now these come from the fact that this imaginary box sits here and is being shoved against this. This part is being offset by the force of the gate back on this water, on this block. But on this block, it's pushing back against this. So this depth, okay, so that depth right there is equal to 10 feet deep. So the pressure at the top of this is 62.4 times 10, or 624 pounds per square foot. That's what the pressure there at this is. Now, this is still 624, but you went 5 more feet down. So this distance from here to here will be 5 times 62.4, because you reach that pressure, you swim down another 5 foot, and that's the additional pressure you felt. So that is 31.2. No.
62.4 times 5 is 312.
312. Yeah, I've got mine. I didn't move my.
You were decimal point off.
Yeah. So
it's added to it.
Yeah.
Added to the original pressure of 624 feet.
Yeah. So now what I'm going to do is I'm going to do this. I'm going to say I'm going to replace both of those. I hate to redraw the free body diagram, but here's what I'll do. I'll do this. I'll say I'm just going to focus on this, a uniform load plus a triangular load will equal to one major load that is 624. That is, in other words, this one relates to that. 624 times the area, which is 5 by 2. Well, that's convenient, 5 by 2. Or 6240. It's just out of luck. I mean, this is purely out of luck. But anyway, 6240 acting right in the center. Now this one is going to be acting a third up from the bottom. believe it or not, it's gonna be 3, 1, 2, times a 5 by 2. However, half of it is gone. So that's 312 times 5.
Times 2.
Yeah, times 2 over 2.
1560.
Okay, so 1,560 pounds. So what I'm gonna do is now I'm gonna go back over to here. And I'm gonna take those loads and put in there. One load is halfway there, and it's 6240, and the upper one is 6240. The lower one was 2450.44.227. The one third over here, that one was 1560. Now, it was a third up, or its distance is 5 over 3 from the bottom. This one distance is 2.5 because this distance is 5, which is the radius here. Now this one's easy because it's 5, so it's 2.5 here. This one is different, and it turns out if you look in the book somewhere, let me see if I can draw this. The centroid of a quarter plate, I believe, is 4r over 3 pi, if I remember right. But a better, well, okay, how about we just, here, we'll do it this way. I know I could find it in the book, but I may do better just of
Quarter plate, quarter circle.
maybe that's it. There you go. I just want to find, if I just find the image, let's see. Maybe I better go down. That's some guy doing, let's see. Usually you can, there it is. So there you go, right there. 4r over 3 pi. So that's the X bar and the Y bar. Makes sense, because, you know, if you flip it over, it's the same. So it is 4r over 3 pi. So let's go back now. And what we're going to do is something really strange. Okay, so I've got everything written there. 44227. Got that. So I'm going to do this. I'm going to go ahead now, and I know I've made that thing kind of tiny down there, so I'm going to try to make it a little bigger. You got a load coming straight down. So what I'm going to do is I'm going to measure from the center here, but I'm also, because of that, I can get the measurement from there. So I've got 6240, that's 2.5. And then I got this one right here, which was the strange one. So this is the 2450.44.227, and it is 4r over, no.
35.
Okay, 4r over 3 pi. Okay, now I have another one, and this force goes this direction, and it's 6240, and it's, okay, so, shoot, I'll measure it from this distance, so 2.5, and then I got 1560, and its distance is 5/3. And I got this force. So let's do two things. I call that a reaction. And then I have the hinge X, hinge Y. So let's sum the moments about the hinge equal to 0. And what you find is, and I'll define that as positive. So the R makes it positive. It's 5 foot away, 5R. And then I'll go through each one. I'll go through this one, this one, this one, and this one. So I'll go through this one next. It is going the opposite way, 1560. And its parallel distance is move 5 minus, so it becomes 5 over this. So in other words, the distance from this line down to this force is not 5/3, but it's 2/3 of 5. So it's 2/3 of 5. Then I got this 6250. It's going the opposite way, so 6240, I'm sorry, now, and it's 2.5. And then I got this one, which is going that way as well, 6240, and it's 2.5. And then I get this one, which is going, that's minus as well. So everything that's happening here, all of these forces are working against this R. And it is 2450.44227 times, that distance would be 5 minus 4/5/3 pi. And you can solve all that and get your reaction force. So that gives you R.
Is that the 5R?
Yeah, 5 times R.
Okay, 5 times R.
Yeah, because that's 5 distance over to it.
Okay.
Then distance down. So what I'm doing is I'm trying to find these moment arms here. So that thing's moment arm is, for the 1560 is 2/3 of the total distance of 5, then 2.5, then this is 2.5, and then that distance is the 5 minus the 4 to 5/3 pi. And so you get a number for that. But here's what's so intriguing. Let's change the way the gate itself was supported. And what we'll do is, this sounds weird. Let's say it was cut. Now let's change the way it was constructed. Here's the way it was constructed. There's a seal right here so that if water does come out, it drips. And then somebody put a metal rod and put the hinge right here. Now, what's interesting is, maybe a little leak here, a little leak there, not much. But let's sum the moments about that point. So we'll say H. So this was H. This will be H2. Now, sum the moments about H2. And we'll make this be positive again. This is what's so intriguing. Okay, so I make this positive. It means these two forces are positive moments. These two are negative moments. So you get two forces here that are pushing this way, two forces that are pushing the other way. So I get two positives. The first positive is 6240, and its distance is 2.5. The second one is positive, and it's 24, 250.44227, and its moment arm is 4/5 of 3 pi. Then I get the two negative ones, negative 6240, and its moment arm is 2.5, and then you get the 1560 times, okay, its moment arm is that distance, or 2 times 5/3. So the first thing you see is that and that knock each other out. The second thing you see is what is the magnitude of that and what's the magnitude of that. And that's why we carry lots of digits.
I'm still trying to multiply the first thing.
Oh, okay. Yeah, that's. Let's see. Did I? Oh, yeah, good. Just out of curiosity. Well, yeah, it says I'm going.
For the first one,
What you get?
13,069.73154. Does that sound about right?
Well, I don't know. Wait, 13.
No, I'm talking about for the whole moment equation up at the very top.
Oh, this one.
Yeah.
Oh, so R was equal to 13.769?
13,069.73.
That sounds reasonable. Yeah, that's a lot. I mean, that's, when you're dealing with water, you're going to end up dealing with a lot of force. It's very difficult to keep
May
water
not
back.
have divided that by 5. I may not have divided that by 5.
Oh, okay.
I'm having to check. Yeah, I don't see it divided by 5. So then you would divide that by 5.
Okay, so we'll just do that.
2,613. Sound better?
Actually, I have no clue.
Yeah, I'll go back and actually
So,
double check.
tell me what these two are.
Oh.
Because this one cancels that one.
2,450.44227 times 45. Okay, so 51,321. 51321.94289.
Oh gosh, 513.
21.94289. 289.
280.
Yeah, 289.
What's this one?
First one, so
1,500 times 20, times 10, 15,000 divided by 3 is about 5,000. So I'm a little, I have to do a little math here. Okay, so first of all,
5,200.
5,200. So let's look at that. Why is my, oh, here we go. Okay, 2450 point 44227 times 20.
5, 3, 5.
Oh, okay.
Come up with the wrong number
On this one.
on that one.
So what did you get on that one? Was it 5,200 as well?
I didn't come up with 5,200, but I'm trying to figure out where I messed up.
It may have been with the 3 and the pi underneath. Yeah, I think that's it. With the pi, you may have put the pi up on the top.
I didn't put that parenthesis around the 3 pi, and that's what jacked it up. Like it tried to times it all by pi,
Yeah.
but yeah. I want to put another parenthesis in it worked.
So when you sum the moments about the hinge in there, this force and this force offset the moment of those two.
And then the other two offset each other as well.
Yeah, so, okay, so the R goes straight through that hinge. This thing goes straight through the hinge. This is no longer a hinge, you just got a pulling force.
Yeah.
But that pulling force would be 5 times whatever that pulling force. Meaning, it doesn't take any effort to open the gate. And that's why, if you go to Lake Darnell, on all these things, all the gates are perfect circles. Because if they're sitting there, because if you look at them, okay, so let me just take this one. So if you look at a gate, it's a perfect circle. And so this is just what the water sees. Say you're down at a certain depth, you're at a pressure, but the pressure gets a little larger, but it's always perpendicular to the gate, meaning all those pass through the center. So none of the pressure force on that gate creates a moment about the center hinge, which is why they make the gates that way. They're making the gate so the water is on the back side.
On the exact opposite of what we
Yeah.
have been working with.
Yeah, so the pressure there goes straight through that hinge. So to open it, all you gotta do is offset the gate. So if you built a gate that was holding back water, and you made it welded some rods so that they went through a perfect circle, then to open the gate, you could just say the gate weighed something, put a balance out there, like a scale, and just move it out there, and the gate will rotate this way, move back, and the gate rotates that way. And so that's why they have those gates that way. This way, in order to open that gate, you got to push super hard up here to have the gate pushed up.
If the hinge was at the wall.
If the hinge was at the wall, yeah. But if you put the hinge out here, it just,
If it's real, in theory, freely.
Yeah. So that's why they build them that way. That's the cool thing about these curved gates is that, people, you can use them to make your life easy. You'll still have a lot of force on that hinge because all that water is pushing that hinge or pulling that hinge. So you just got to make sure that you got a good support system. So if you look out there at Lake Darnell or wherever, They have a big concrete pillar. I'm not sure I can draw it, but I can draw kind of attempt it. You got a big concrete pillar here, and here's your gate back behind it. Kind of at the next concrete pillar. Oh man, there's a concrete pillar next to it. Oh gosh. And you've got a pin in those concrete with a bearing, hopefully, that makes it so that gate can swing open and close. But if you notice, these big concrete pillars are what's holding the weight of that hinge. So if you have some, and I'm pretty sure they got some really high level bearings right there, probably that big or bigger, that are sitting there, and all you gotta do is, I'm sure they got little motors on there, so they just turn, eek, eek, and it just does a little bit, opens it or closes it. But the key is, you gotta offset the friction of the hinge and the weight of the gate. If you have it balanced, so that that gate, if there was no water behind it, it just sat there wherever you were at. Then when you put the water behind it, it just produces force on that hinge. All you got to do is turn it. And then it becomes an easy thing to open or close that gate. As long as, the concrete doesn't crack or there's anything like that, as long as you got that issue. If you did have that issue, you'd have to, I guess, I don't know. I guess you'd put a wall around behind the gate and fix the gate, I guess.
That's one thing I've always wondered about building the dam. It was a river before they put the dam there.
Yeah.
How'd they put the dam there? Because concrete don't set up underwater.
What I figured is they put things around it, and like the Golden Gate, what they did, the concrete will sink. So if you put it down in a tube and just pour it, the concrete will go down in the tube and shove the water out the top. Now I've seen people do that.
Yeah, like pilings.
Yeah, and so it shoves the water out the top, and pretty soon when you put enough concrete, it's all filled with concrete, and then you just wait for it to set up. Then your issue is, what did you put around it? And do you go in and take it off, or do you just not even worry about it? Like if it's old pieces of plywood or something that you've shored up, eventually they'll rot, maybe. I don't know. Maybe they won't rot.
Okay.
I know I saw a special on them making the Golden Gate Bridge, and that's kind of what they did. They shoved down into it, and they just poured the concrete, and it started making the water come out the top, Although I would think if you were not careful and it got all mixed up, you might have problems there. I don't really know. Because, there's water in concrete, and you got to get it to dry out to set up, so.
I can understand how they build concrete stuff and drop it into water. I can understand that easier than I can building concrete underwater.
Yeah.
It gets so much more complicated, I can tell.
I can bet you we could probably find, let's see. I think I saw it on the I don't know. I think I probably saw it on one of those History Channel or something. This is a commercial, and there's another commercial.
In the 1920s, long before the technologies and advancements of today's rise of cars and the growth of San Francisco during these authorities insisted that he could only proceed. The Department of War even pushed for the bridge to be painted black with yellow stripes, north of the bay. In a remarkable structures weighs 22 by steamer ship travelling in the fog. At the end of the pier, pilot bombs were dropped down shafts to break up the rock under the seabed. Seagulls swarmed over this operation. This pier was destroyed twice during the works, once by a storm and again by a steamer ship travelling in the fog.
Traveling in the fog.
At the end of the pier,
The end of the
pilot
pier,
bombs would drop
pilot
down
bombs
shafts to
would
break up
drop
the
down
rock under the
shafts to
seabed.
break up the rock under
Seagulls
the
swarmed over this
seabed.
operation as stunned fish floated to the surface. With the bedrock loosened,
Okay,
the area was
bedrock
dredged
loosened, the area
before the
was
first
dredged
underwater concrete pour.
before it,
The area was then pumped out, and the remainder of the
and the
concrete was
remainder
dry
of the
poured.
concrete was dry.
Simultaneously, the
Okay.
concrete anchorages that the
So
suspension
that
cables
means
would
they
connect
sucked
to
out
were cast
the
on either
water
bank. The
as
scale
best
of
they
concrete
could,
being poured
probably.
across the bridge site led to an
You can
on-site
kinda
mixing
see
plant being
a
established,
little bit of a,
which the suspension cables would connect to were
calls
cast on
it
either bank.
like
The scale of concrete being poured
Right.
across the bridge site
there maybe. I bet you that whole thing was completely sealed, and they sucked the water out, and then they probably sent a truck over or something to dump the concrete. It's a lot of concrete.
led to an on-site mixing plant being established.
Let's see, there
With the
may
southern
be
footing in place, the steel
better
south
pictures
tower was
than
erected.
this.
The next step was to suspend cables 3 times over. Fire back and forth across the bridge began, eventually forming the bridge's 2 main
Oh, that's
cables,
cool.
each
There's
3
no
feet wide in
bridge
diameter.
platform at all.
Wooden pallets were then hung beneath the cables,
Did all the
creating a
cabling.
catwalk for workers to weave, compact,
There's
and
several
bond the wires
bridges in Arkansas.
before painting them to
Matter of
create a
fact,
watertight
I
seal.
visited one
With the main cables in place,
recently.
smaller vertical cables would
Mountain
drop down
View,
towards
just
the
north of
water.
Mountain View, that
Steel
have
trusses
these
were then attached to them,
cabling
creating the
setups.
deck for the concrete roadway to be
Because
poured
about
on.
that time, the Golden Gate was put up. There was a lot of bridges there.
Throughout the construction process, many workers progressed. So too did the debate around what construction work started, and with 600,000 steel rivets in place, the bridge deflected by 10
and they
feet,
threw another
flattening
party.
out under the weight of the crowd. This extremely dangerous
Oh my
incident
gosh, look at all those
has led
people
officials
up
to
there.
commemorate anniversaries in different ways ever since. The bridge has been a huge cultural and economic success since
They opened a small bridge in this little community somewhere in Africa. And they cut the ribbon on it and the thing fell apart because there were so many people on it.
Oh, no.
But as soon as she went, snip, it went.
Oh, gosh.
And it was over just a little bitty creek kind of thing.
Yeah.
I don't know if people were hurt, but it was quite funny. As soon as the ribbon got cut, snip, it's like the whole thing was held together by that one big ribbon.